right, welcome to electric field examples. Okay, I have uploaded, I'm doing this one a little bit differently to the last video. I didn't really like how that turned out, so what I did was I sat down and actually wrote some detailed responses to the questions. Okay, and as I was doing it, I realised, well, these, I've actually done them pretty neatly, and they kind of, look good. And so what I'm going to do, or I would have done by the time you see this, is I will have uploaded to Compass Resource and OneNote copies of this, scans of this. Okay, so at any point that when you're doing questions in the chapters that I sent you in the mail, if you're getting stuck on something that's horribly difficult, you know, you're like, I just don't get it. Okay, then you flick open to these and you can see I've put in a lot of, where necessary, a lot of notes and a lot of details, little pointers, and this is what you do and this is why you do it, right? To help you figure out how it all works. And if that doesn't help, then just, text me and say, hey, I looked at your answer, I still don't get it. Can you explain it in a different way, and I will do my best to do that for you, okay? All right, so question one, it's good to go through the early questions because it sets your mind into the right sort of zone of doing these sort of things and getting you thinking about what you need to. Now, at this point where if you're going through this stuff, you need to go, okay, where's your help sheet? Where's your pen? Where are your notes? Everything, your calculator, not the goddamn CAS calculator again, okay? I know there are a couple of you still using it, don't. Okay? All right, question one, let's go through them really quickly. An electric field line that connects 2-point charges is only possible if, this is what they mean. A field line that connects two charges. That does not happen if you are looking at, where are you? If you are looking at, is this it? Yeah, if you're looking at two like charges, for example. See the two like charges? There is no possibility of a line directly linking them. That's what that question's about, okay? So, that is why I drew that, so you can see one charge is positive, one charge is negative. That's the only way of doing it. Beautiful, easy, move on. Okay, question 2. A point source P is positioned on the grid as shown below. P has a negative charge of Q, so whatever, doesn't matter. Which of the points below represent equal electric field strength? Okay, the only way of doing that is, now the reason I've drawn these lines in here, it says it is a negative charge, which would mean technically I should have little arrows, all right? And they radiate out from a point charge uniformly. So the only two areas or regions where you can definitely say the field strength is the same is A and G, okay? So you look at A and G, they are equal distance at the same angle, all right? Now technically, B and H are correct, and so C and I, they are also, okay, because they're the same distance apart if I'm using my logic brain properly. But the reality is only A and G out of all of these is actually correct, so none of the others matter because they're not there as options, all right? So that's what they mean by this, and there's a few versions of this question as you go along. All right, so over here, I didn't do this one. It's essentially the same thing. Didn't do this one. You can see the ones that I really want to focus on. I've put a bit of highlighter on. So this is question 5, and 68 questions, and I want to be here like forever. All right, so, all right, this one. 3 electric charges. Now, notice Q minus, Q plus, and little q plus, all right? They're placed at the vertices of an equilateral triangle. Equilateral triangle. Every little bit of information they give you can be useful, okay? Which means, equilateral means, if you don't know, these two lengths are the same, all right? They're all the same distance apart, okay? So that also means that they're also at 60 degrees to each other, because 3 6s are 18, 180 degrees, okay? So equilateral, when they say equilateral, it's important, okay? Because it means the distribution of forces will be very predictable, okay? Now, it asks, which of the statements A to E below correctly describes the direction of the total force exerted on charge little q? Now, little q, you can see, will try to go in this direction because of this q, okay? Why? Because they're both positive. They're both positive, they're going to be pushing, all right? So the way this works, the easiest way to comprehend what's going on here is don't worry about what's going on here between these guys. You just worry about what is the force specifically from this point charge. That way you break the question down into nice little bite-sized bits and then it makes sense. So this one is pushing in that direction, directly away. This one, this one wants to move towards negative q because they are opposite and their force therefore is attractive, not repulsive, which means it wants to move in that direction. Now, both these q's are the same, denoted by the same letter. So in other words, their charge is the same magnitude. This means that the force that this particle, whatever it is, whatever charge it has, or whatever the magnitude of charge it has, is in that direction from this one, and it's in this direction from this one. And check out this nifty little adding vectors thing. If you've got two vectors that are pointing away, what you can do is draw a little, this speeds up your vector additions really well. You draw a parallelogram, okay? So the parallelogram is this line here, this vector here, is drawn there, but you do your sort of dotted line, which is the same as this. This one is the same here, okay? Dotted line, all right? Now, this one's pointing this way, which means it has a component going this way. This one's pointing this way, it has a component going this way, all right? The sum of the forces is through here, okay? So you can see that the vector sum is really easy if you do it that way. And in fact, they do it a lot throughout this work. Now, let's interpret the answer though, because I love how the answer has been stated. Which of the following statements best describes the sum of the forces? All right, so basically the sum of the forces, I've moved it so it doesn't look good. One sec, there it is. Its direction is at right angles. I'm just going to look at D. Its direction is at right angles to the line joining charges big Q and the two big Q's. Perpendicular at right angles to the line joining. So is that at right angles to this? No, okay. It's not, all right. Its direction is parallel to the line joining charges big Q and big Q. Parallel to that line, to the line joining this. Yep, there you go. I know that there's probably 8,000 easier ways to ask for the answer, but there was a lot of language in that, and I do know from experience that some students look at that and go, what the hell are they talking about? Parallel to the line, what? You know, and you end up with sort of getting it right and still not being able to put it down right, okay? Okay, so the next one, question 6, okay? Question 6, very similar. Consider a point P equidistant from two charges, plus Q and minus Q. So you've got the two charges, and what I did here is I drew in my field that moves through this area, okay? Now, traditionally, that's all I really do, okay? I'll look at the field, at the shape of the field. With a bit of experience, you tend to get it right 99% of the time. And you can see that as this is in the midpoint, that these lines are gonna, they're gonna have their maximums around through here, okay? So anywhere this point is, this point is not a charge, it's just a point in space, okay? Anywhere this charge is, along this line, exactly middle, the field is always travelling this way when it goes past it, okay? So that's what I would do, and, you know, it gets the answer, right? So the electrical field at point P will be, what? Parallel to the line joining the charges, yep. Parallel to the line joining the charges. The way they would do it, and which is probably more mathematically better, right, this is a negative charge, okay? So let's see, consider a point P equidistant from two charges. Okay, this is a negative charge. All right, this is something that I picked up from my own sort of work. When they ask about, a point of empty space, all right, which they did in this case, this is consider a point P. They haven't said it's a charge, they haven't told you what the charge is, they haven't told you anything about it, it's just empty space, right? The tradition is, or the convention is, that when you're answering a question like this, that you imagine a small positive charge in that empty space. That was the advice given in a bunch of stuff that I've read and other things that I looked at. Put yourself there a little positive charge and ask yourself what would happen to it in that field. So if that's a little positive charge, you will notice that because that's a negative, okay, and the field is moving in this direction, that it would find an attractive force in that direction. Because this one is positive, it would be a repulsive force if this was a little positive charge, okay? Again, you get the same idea where this vector and this vector are equal in magnitude because these charges are the same, all right? And the sum of these vectors is straight out. Gives you the same answer. It's more, I guess, more mathematical. And it also gave me an excuse to mention that idea that even when they often talk about a point in empty space, depending on how the question is phrased, sometimes you need to imagine a tiny little positive charge up there and say, well, which way would it go? Okay, and that's how you tend to answer those questions. This is actually an incredibly easy question. This was done in 1967, years and years before I was born. It was worth 1 mark. Less than half of the state at the time got it right. Super easy. Don't know why anyone would struggle with that one. Okay, this is an interesting question. This is why I added in a whole lot of stuff to your help sheet, which wasn't really stated anywhere that it needed to be there, okay? So, for example, this question here says, another one, 1966, all right? I know that Colin adds these questions in because things like this you'll probably never see in an exam or a SAC, but they do build your understanding of what's going on, and I think that's the point of including things like this. So 2-point charges plus Q and minus Q are a distance 2r apart. So what I've done here in all my little writing is these are the 2-point charges. They're coloured in red, okay? And there's a point A, which is exactly halfway between them, okay? Now you've got a couple of points B and D and C out here, and there's E out here. And it's going to ask you what the electrical potential is at certain points. Now, electrical potential, the answer given by the notes is, if you look at the first question, which of the points A to F is of 0 electrical potential? And the answer is like, well, it's 0 electrical potential, it's A, because it's halfway in between. And I'm like thinking, that's not a Y, that's just it is, right? So I went and investigated a little bit and found that to calculate the electrical potential, can you see it on the board here? You need to use this formula here, okay? So basically what you want to do is know what the electrical potential is, or the sum of the electrical potentials at A would actually be, right? So you can do that by making this calculation. So what I did was, let's see if you, what I did was I used KQ over R. Now K is just K, and Q is just Q because those charges are actually specified. Even R is simply R, okay, because you've got 2R. So you barely have to really do anything except for keeping in mind one of these is positive and one of them is negative, okay? So there is an electrical potential between them, okay, but what is it exactly in the middle between them? Well, the electrical potential due to this charge, okay, is KQ on R, right? So here it is, Q on R. And it makes sense when you calculate, and that's R because that's the distance between this charge and this charge is R. Oh, sorry, wrong R, this R. All right? Now, it all makes sense when you calculate the electrical potential from negative Q. At negative Q, it is K times negative Q over R. So what essentially you end up with is, on this side, KQ on R, and on this side is minus KQ on R, and the potential is the sum of the potentials. So when you add these two together, they cancel out, and you end up with zero potential between them, okay? So that's a kind of a nice little mathsy explanation of why, at this point A, the sum of the potential is zero. Because it's not that it's actually zero, it's the sum of the potentials is zero, okay? So, this way I've got to explain that, all right? So, the rest of the questions are easier. So, for example, when we move on to question 8, at which point is there the largest positive potential? Okay, the largest positive potential is as far away from the negative as you can get. Okay, so the line from here to here is the longest line that there is, even considering being D. Okay, the longest line from Q joins C. All right, so that is where the greatest positive potential is. And again, if you did the calculation, if you did the same calculation with that Q and that point, you end up finding, that no other line gives you a value higher than that because of the R that's involved, all right? So that's kind of that question there. Which 2 points are at the same potential? And that's another question of symmetry. They are the same distance away from this charge, and they are also the same distance away from this charge. So it means that these 2 points are in equal electric fields, or they have equal electrical potentials because of their separation. All right. Now, what was the next thing that I felt was worthy? Okay, this was question 11. I chucked it in mainly because it had a reference to picocoulombs. This is something that I didn't put on the help sheet, but you really do need to, is make sure that you have a comprehensive list of what nano, pico, micro, milli, tera, mega, kilo, what they all actually mean, all right? So that's really, really important. Find the strength of the electric field 3 millimeters from a 4.5 picocoulomb point charge. This is asking you to find the electric field strength from a point charge, which is this formula. It's right on your help sheet. It even should say exactly what it's for. But let's see. Oh, it doesn't give us a percentage of kids who got it wrong. A lot of kids would have gotten this wrong simply because they can't handle numbers properly. Okay? And forgetting that 3 millimeters is 3 by 10 to the negative 3 meters, and actually putting in the values correctly. Also, pico is 10 to the negative 12, so 4.5 times 10 to the negative 12. You've got to get that right if you want to get the question right. And then down here, I said, don't forget, this is newtons per, notice newtons per coulomb is the answer is given in. That might throw you if you're like, oh, this is electric field strength. Why is it not in volts per meter? Are you thinking, am I missing something? It's like, oh, no, you're not missing anything. They're equivalent units, and I put that in the help sheet, and I've actually highlighted here in the question so you don't mess that up, all right? Okay, next question 12. Next question 12, when 2 small electric charges are held at a fixed separation, they exert a force of attraction on each other of 50 newtons. To obtain a force of 200 newtons, you could do what? Well, you look at the formula that tells you what the force due to the 2 charges actually is. So F equals KQ1 Q2 over R squared. Beautiful. Now you're going to say to yourself, well, I've got to go from 50. That's 50 newtons. That's got to go to 200 newtons. So I've got to go 4 times more. What can I do out of the 4 options that they've given us which one of those will work? So you look at option 1, double the distance of separation. So if you double the distance of separation, making that bigger makes that smaller, does the exact opposite of what you're asked. Okay, halving both charges, again, making that smaller does not make that bigger. All right, double one of the charges. Well, that'll get you halfway there. Double the size of both charges. So I chucked the 2 on both of these, and so this is an equals here, so 2 times 2 is 4. So you multiply, that goes up by 4, that means that goes up by 4 to keep the equals. All right, so double both charges is the only one of those options that will work for what's been asked. Down here, same exact question really, except that there's just a bit of mucking around with fractions. You really do need to know fractions really well, okay? Who knew, right? When you were learning them, that fractions were going to be useful. So 2 electric charges are separated by a certain distance and experience force of repulsion F. If the distance between them is reduced to a third of its original value and one of the charges is doubled, what is the new force? So again, this is the force between 2 charges. You write the force equation down and then do what they say to do it. So you double one of the charges and you take a third of the separation and see what that effect is. So the difference here though, when the separation changes, it's an inverse squared law, so you actually, taking a third should, bringing them closer to a third, should multiply the force by 9 on its own, okay? Which is what you see here, all right? Doubling the charge gives us 2 times 9, all right? When you're doing, manipulating your fractions appropriately, okay? So you can see here, 2 times 9 is 18, so the force goes up by 18 times, all right? So Dan, 18F is the correct answer. There you go. And it's just, I only included it because it's got a lot of fraction stuff in it, which I know sometimes people struggle with fractions, all right? So this one's another good one. Again, there is no way that this is worth 1 mark. Okay, there's just, seems to be a lot of thinking involved in this question for 1 mark. So we've got here big Q, they're both positive, so they're pushing. This is a small q, so basically saying that it doesn't have to be, in this question 14, it doesn't have to be the same size as big Q and that big Q. It could be smaller, could be bigger, doesn't matter. The point is that this charge is going to feel a repulsive force from both of these, okay? Obviously, from what we've learned and studied, that it's going to feel a hell of a lot more force from X than it is from Y. So it will, just looking at this, it will experience a sum of the forces that will be going that way, all right? Has to, okay? A small positive charge plus Q is placed on the line between X and Y, a distance of 1/4 d from the charge at X, okay? So, which of the following, so what I've done, I've color-coded it to make your life a little easier. Which of the following expressions gives the magnitude of the force experienced by the charge at plus Q? So you need to figure out what is the force due to X on this spot and what is the force due to Y on this spot. And when you work out those 2 forces and that they're both in opposition to each other, take the big one and take away the smaller one, and that's your sum of the forces. All right? So this is what I've done here. The blue curly bracket refers to this calculation. The light blue curly bracket is this calculation. Notice I've been careful to put a minus in there because it's going the other way to this one. All right? Because they're both pushing towards. Okay? Find the sum of the forces. Again, this is very much just fractions and some basic algebra. All right? To get down to the correct answer, to get down to this monstrosity here, you can't afford to skip things, mess things up, forget how to do your fractions and all that, all right? So, okay, that's actually, I guess, difficult question based on manipulation. If you're good at manipulation, it's actually quite an easy question. All right. So question 15, let's see. If the small charge is now placed at point P, precisely midway between X and Y, which of the following expressions best describes the net electrostatic force on it? So what's the sum of the forces? There is no force like that. I don't like that. There is a force from both, okay? It's just that the sum of the forces is 0. Writing there is no force on it is ugly, because that just implies there's no force in that area, and there clearly is. Alright, so, but it's the most correct answer. Okay? Moving on, did I do this one? Nah, uniform. Alright, uniform. Let's see, anything interesting down here? Yep, here we go. This took me time to get my head around, because you have to really think about what the question's asking and separate out. You know how when you guys were doing projectile motion, it was you really had to separate horizontal and vertical components of motion, otherwise you really couldn't work anything out. But in this case, you kind of have to do the same thing, but then in terms of forces on charges, and it becomes a super complicated diagram. So what I did was, if you look at your diagram, it's much cleaner. They've got 2-point charges, okay, and then they've given you 2 lines, one that bisects them this way and one that travels past them this way, and then a nice little set of axes, y and x, or xy axis, to tell you what they're talking about when it comes to the forces that are being felt, okay? So 2 fixed spheres, these guys can't move, but you take now a positive point charge and move it along here, okay? Now you can see that as it moves this way, it is going to feel a repulsive force that it just does not want to be anywhere near this guy here. They're both positive, they just don't like each other, never gotten along, okay? And as you move it along, it's like weak, stronger, away, and then it's going to get away from this guy and go, oh, okay, this is better, this is much better. As it's getting closer here, it's going to find midpoint between the repulsive force and the attractive force of this. Now, what we're really considering here is the force that it's feeling in the y direction, okay? So here, if you imagine a repulsive force this way, there is a component of that is in this horizontal direction, and then a component of it is in this horizontal direction. This vertical direction. All right. So, what this question is asking is the force in the y direction. Force in the y direction. That's all they care about. We don't care about this force here. Okay? So you can see that as this gets closer and closer, the y component is getting bigger and bigger. Now this took me like time to get my head in the right place to even consider this correctly. Alright? So you can see that as it gets past here, when it's right there in front, then it's all y. Okay? Then as it goes over here, it's got a force going this way, okay, which is now split between this y component and this horizontal x component, okay? And the further it goes, you can see that this y is now, when you get to, it's getting now smaller. It's smallest out here to nearly nothing. It gets a max out here, and then starts to get smaller again. So it's small out here, it gets to a max out here. Now in the middle, if you look at it right in the middle, you will have a force repelling it from this direction, from this guy, okay, which will give a certain y. But because it is the same distance away from the negative charge, and the negative charge wants it's got a force going this way, okay, but it's the same. It's the same. That vector should be the same as this vector. So if they're the same because they are equal charged, then the y component at this spot, you can see the y component cancels beautifully with the attractive force from this guy and the repulsive force from that guy, explaining why this bit's right, this bit's right, this bit's right, but is this bit right? Now, keep on moving. The force here is the maximum, but in the other direction. It really wants to be there. So there's the force in the other direction there. All right? And then as you go off to infinity, you lose it. Okay? Using those vector sums makes the question way easier to interpret. Okay? Now, that's cool. You can do the same thing for the other one. Now, for the other one, it's really interesting actually, because you start your positive charge here, equal distance. All right? So it's being pushed by this one and pulled by this one with equal force, because it's always the same distance from both. As it moves along this line, the distance from both is always the same. So the forces experienced are always the same, except that one is a push and the other is a pull, right? So the thing is, but because they're always the same, the y components are always the same. Hence, thus, therefore. The answer is F. There is no force in the y direction as the particle moves from here to here. Okay? Right. How good is that? Again, a lot of physics is logic based. Okay, and that's what people find frightening, and why a lot of people won't choose it, because they're worried, what if I'm not logical enough? Okay, but I found I'm not the most logical person in the world. I found that if I stare at something long enough, eventually it gets to,